All right, this section is all about solution sets of our linear systems. Now, this first idea is going to sound vaguely familiar if you've ever taken differential equations, and that's the idea of a homogeneous linear system. So the homogeneous linear system basically says that we're going to set the system equal to zero. And in this case, because we're talking about matrices and vectors, we're going to set our product here, the product of our matrix and our vector, we're going to set that equal to the zero vector. And there's some really nice properties that are going to happen when we do this. So one of the properties that happens is that this system is always consistent. So what that means is that there is always going to be at least one solution to this system. And that one of those solutions is always x equals 0, or the zero vector, right? Which makes sense. So it doesn't matter what my a is. If we think about if I have a, b, c, d times the zero vector 0, 0, I get 0 times a plus 0 times b gives me 0, 0 times c plus 0 times d gives me 0. So I get the zero vector. So this is always going to be a solution. Now, there may or may not be more solutions. So either there is one solution, and we actually call this the trivial solution. So the solution, x equals the zero vector, is called the trivial solution. You know, it would probably help if I just, oh goodness. All right. Let's just move some stuff over there. Of course. Why? All right, never mind. I'm gonna spend all day doing this. So, okay. It's called the trivial solution. And we call it trivial because it's like, okay, yeah, duh, right? That's pretty uneventful, pretty boring, right? So we call that the trivial solution. And our last property has to do with whether or not we have a non-trivial solution. So we say that the homogeneous system, ES system, has a non-trivial solution if and only if and only if. So the nice thing about an if and only if statement means that we can use it going forwards and backwards. So we can prove the first, if we show the first statement, it implies the second, or if we prove the second statement, it implies the first. So the homogeneous system has a non-trivial solution if and only if the equation has at least one free variable. One free variable. And we can determine this by the number of pivot points. So in other words, if the number of pivot points is equal to the number of variables, then we would have, then there's not going to be a trivial, or there's not going to be a non-trivial solution. All right, so here's some examples. So in this first one, you'll notice in each column, so here's my leading entry, here's my leading entry. It doesn't matter that I have 0, 0, 0 down here. I only have two variables, which means that because I only have two variables and I have a leading entry that's a 1 in each of those, or just a leading entry in both of those, that means that I have no pivot points, which means that I don't have a non-trivial solution. So this means that the only solution is the trivial solution. So 0, 0 is the only solution. And you can see that here, right? This says that x1 equals 0. This row says that x2 equals 0. And that's it, right? There's no other options there. Now in our second one here, so there's a pivot point. In my next column, you'll notice that I don't have a leading entry in that column, which means that I have a free variable here, right? So I have a free variable since there's no pivot point there. Or in other words, I have 4 variables but 3 pivot points, which means that x2 is free. So that means that this system has infinitely many solutions, right? Because there's always going to be at least one solution, so it's always going to be consistent. So if I can show that I have more than just the trivial solution, then that means that I have an infinite number of solutions. And we can see that here. So this tells us that x1 equals x3, or x2. Let's try that, -3. Oh, Jesus. Let's try that all again. x1 is -3x2. And then all the other ones, x3 and x4, are both 0, but this gives me some relationship between x1 and x2, which means that I have an infinite number of solutions. And last but not least, our little friend over here, we have 3 variables. We have a pivot point here. In our next column, we don't have a leading entry. In the next one, here's our leading entry. So I only have 2 pivot points, but I have 3 variables. So that means that x2 is free. And then I have infinitely many solutions. Ta-da! So we're going to use this last example here. We're going to use our 1, 4, 0, 0, 0, and 0, 0, 0. And we're going to write this as a general description, right? So we talked about that last week. We can also call it a parametric description, right? So this tells us that our parametric description says that if I look at that top line and I solve for x1, so I'm gonna isolate each of my free variables, or describe everything in terms of the free variable. So this says x1 is equal to -4x2, right? That's that first row there. We know that x2 is free because there was no pivot point there for the x2 columns. No pivot point, x2 is free. And then this next column is actually, or the next row here, the second row is where we get the x3 value. This tells us that x3 is 0. And actually has no relationship to x2. So x3 is constant, it's always going to be 0. And the x1, x2 are is what's going to change and determine what our solution to each system looks like. So what we're going to do is we're going to put this in what we call parametric vector form. And for parametric vector form, what we're going to do is we're going to actually write this as a system, as an equation. And what we're going to do is write it as an equation that, so this was parametric description. And in parametric vector form, what we're going to do is I'm going to write my variable matrix, x1, x2, x3, right? That's my solution matrix. And I'm going to describe what it equals in terms of my free variable. So that it equals our x2, and I'm going to think about x2 times what is going to give me x1. Well, x2 times -4 gives me x1. x2 times what gives me x2? Well, since x2 is free, x2 is itself, which means I'd multiply it by 1, right? 1 times anything gives you anything back. And the last one, to get x3, since x3 is defined as 0, x2 times 0 is the only thing that's going to give me 0. So I can define this as a, so this is a variable times a vector. And what we typically end up doing here is we redefine that variable. Instead of x2, we're going to define that variable as like t or s. So what this boils down to the vector equation. X vector is some variable, doesn't matter, times the vector v, where v is this vector -4, 1, 0. And it turns out that this is the equation of a line that goes through the origin. Now, it's the equation of a line that goes through the origin, and we can use this vector to define it. And this is actually a three-dimensional vector, but in this case, because x3 is 0, that actually means we don't have that third dimension in play here, at least in terms of this this line. But this would be the line if we thought about it in 3 dimensions here. Where this is x, y, and z. So we're going to go -4 in the x direction, 1 in the y direction, nowhere in the z direction. There is the terminal vector, so there's our vector v. And if we think about this, so this is, I know it's hard to see and imagine. So this is the line x equals tv, where v is this vector here. This guy. So it's a line. So anywhere, so if I take, basically we're taking any multiple. So this says that that the x value, or the x solution vector, is any multiple of that v vector. That's all that's saying. And this is parametric form here. Now, again, often we might rewrite this as a t instead of an x2, but that's it. All right. Okay, there we go. We were talking about a homogeneous equation here. It was homogeneous because these were all zeros. So this is homogeneous. Yay. Well, who are you? Where am I? I don't know. All right, so here's my, here's a fancier way of saying parametric vector form. So it doesn't necessarily have to be just an x and a t and a v. This happens to be true. This will happen as long as we're talking about the homogeneous equation, right? So I don't know what that means. So if you think about this looks vaguely like the equation y equals mx plus b without the plus b, right? This looks a lot like where our m is kind of, this is sort of our v vector sort of determines our slope, or is really sort of determining the direction that our line is going to go in. So this is always an n-dimensional line that goes through the origin. And what that means for us is that if I have a non-homogeneous system, it is possible that I could have a shift where I'm going to shift that line or a plane. So if we were in this form, if it turns out that I have more than one free variable, I can have as many free variables as I want, and they each get their sort of, so this example right here has 2 free variables. And this describes a plane. Yay, planes. So that one describes a plane instead of a line. But if I have a non-homogeneous system that comes out to be that has a vector that's not multiplied by a free variable, so in other words, I have some other piece there, then we can think of this as like the b in y equals mx plus b. Now, it's not really the b in terms of like, that's not, I mean, it is, yeah. I'll show you a picture in a minute. But that b there is sort of like, that's our shift up or down. So this is a shift that happens where it takes our entire either plane or a line or whatever our solution type looks like, and it shifts it up and down. And that's really, yay, linear equations. They're so exciting. Now, let's go back to that example and let's look at the non-homogeneous version of it. So now you'll notice that these are not zeros. So therefore it's not homogeneous. But it's already been row reduced. We don't have to worry about that. So we are in reduced row echelon form, or not quite reduced row echelon form, but we're row reduced, and that's great. We have a free variable here, right? So we still have our free variable. And if we write it as a general equation, you can see that x1 is 2 minus 4x2. Right, so all I did was I applied this. So we had 1, or x1 plus 4x2 equals 2. All I did was solve for x1. Again, we know that x2 is free. And we know that x3, this time, x3 is not 0, but x3 is 3. So how are we going to put this into parametric vector form? Again, we're going to think about, so because we have these extra constants, right? So this is a constant, but it's not a constant multiplier, which means that that value does not change based on x2. Same thing here. This is a constant, which means that that value is not going to change based on the value of x2. Or x1, x2, and x3 might, but so we have constants. So we can write this in parametric form, or parametric vector form, by saying, so x1, x2, x3. And again, I'm gonna express this as two different vectors. So I'm gonna start with my p vector here and think about what are just the constants there. So this first one has a constant of 2, and it's not multiplied by anything. So you'll notice I have nothing out in front of my vector here. I'm not pulling anything out, so it's just a constant of 2. My x2 is free, which means that I don't actually have any constant multiplier or constants that are being added or subtracted to it. So that one's going to be a 0. And then the last one, my x3, 3 is a constant, and it's not being multiplied by an x2 or anything else, so it's just a, so I'm going to put that 3 there. And then I have, and I'm going to pull my x2 out, and then I'm going to express what vector would give me back all of those other things. So again, I'm going to have a negative 4 here. Negative 4 times x2 gives me back my negative 4x2. You get the idea, right? If we backtrack this, do I get back to these sort of separate individual equations? X2 needs to be multiplied by itself so that I know that x2 equals x2. And x2 is going to be multiplied by 0 because there is no x2 in the x3 equation. So here we go. So there's our, so this tells us that 2, 0, 3 is our p vector. And oh, that should have been a vector up there. Whoops. And that this is our v vector, and we get the lovely equation x equals p plus tv here. Yay! All right. Lovely theorem down here. And there's not much, so I have some pictures here to sort of help us understand this theorem. But it's important to remember, so I didn't do a great job of talking about our span here. Last week, I'm still, processing. So the span of a single vector just means that this is every multiple of v, right? That's what the span is. It's every multiple of it. So that's I can have a vector going this way. We could have a vector going this way. In other words, the span of a single vector is a line. In that is a line that goes through the origin. So that's important. So this is the line. Yay! Yay lines. Now, if I have two different vectors, so we did kind of talk about this a little bit, right? We talked about the linear combinations of two different vectors. We did a little example, but I didn't explicitly state that if I have two different vectors, their span is equal to a plane that contains both of those vectors. So any combination of those, so any linear combination of u and v is going to be within that plane. If any, in fact, any vector that I can draw that's in that plane is going to be within the span of u and v, right? Or it's going to be some linear combination of u and v. So this theorem here says that suppose the equation a x vector equals b vector is consistent. So again, we have some solution there. So it's consistent for some given b. So I have a solution, and p is some solution to it. then the solution set of A, x equals B is the set of all vectors of the form W equals P. So this is that some solution so this is our solution to AX equals B. And then we can add in the vector H, where the vector sub H is any solution of our homogeneous equation. So essentially what we're doing is we're saying that if I take, so representationally, if we think about our solution set to this vector, we're either going to get the trivial solution, which is 0, 0, 0, or we're going to get every solution. And now, if that solution is a plane, so if I have two free variables, that solution is a plane, right? We just talked about that up here. So it could be a plane. If I have two free variables, if I have a single free variable, then my solution is a line. But either way, to the homogeneous equation, it's going to go through the origin at 0, 0. So in other words, we're talking about a span of V or a span of U and V. So again, do I have a single free variable or do I have multiple free variables? If I add my P vector, which is some solution to this one, what that's going to do is that's going to take the homogeneous solution set, which in this case is this particular plane, that green plane, and it's going to shift every point in that plane up to the P, up by that P vector. And now that P vector may be vertical, there might be a little skew to it, but either way, all we're doing is we're creating a parallel solution set. And that parallel solution set is the solution, is a solution set to AX equals B. Hope that makes sense. So in terms of thinking about this, this is all the solutions to our homogeneous. That would be V sub H in this case. And then this is all the solutions to our non-homogeneous equation, which is this one, and that is our V sub H plus our P, so it's just shifted up by, so shifted by P, right? So P specifically applies for that B, that, yeah, anyway. Again, if you've taken differential equations, that idea is going to sound very, very similar, right? We've talked about, yeah. All right, before I trip anymore on my words, we're going to come back for the next section.